Hello there and welcome to the Silent Science. I'm so glad you're here tonight. We're going to drift gently through the swirling skies above us as we unravel the secrets of weather those. The sky that holds your dreams. It's not just empty space above us, it's a living, breathing system, constantly shifting, shaping the world in ways we rarely notice until the wind howls or the clouds gather. But have you ever wondered what sets it all in motion? What unseen forces guide the breeze that rustles through your curtains at night or the gust that sends leaves swirling down the street? Imagine for a moment that you're floating high above the earth, watching the atmosphere swirl like an endless ocean of gases. You'd see currents of air moving in great spirals, rising and falling in patterns so vast they span continents. This isn't chaos, it's a finely tuned dance, orchestrated by heat, pressure, and the spin of our planet itself. And yet, despite its scale, it begins with something as simple as warmth from the sun.
What happens when sunlight touches the surface of the earth?
How does that energy transform into wind, rain, and storms? These aren't just abstract questions, they're the foundation of every weather story written across the sky. So take a deep breath, let your thoughts drift, and join me on this quiet journey through the science of the atmosphere.
The sun est invisible.
The sun is more than just light, it's the silent conductor of Earth's atmospheric symphony. Every gust of wind, every drifting cloud, every storm that rumbles across the horizon begins with its touch. But here's the twist, the sun doesn't warm the air directly. Instead, it warms the ground, the oceans, the surfaces of buildings and trees, and even the asphalt beneath your feet. These warmed surfaces then radiate heat upward, gradually warming the air above them like a stovetop heating the kitchen air after being turned on. Now picture this process playing out across the entire planet. Some regions, like the equator, receive direct, intense sunlight year-round, while others, like the poles, get only a slanted, weakened dose. This uneven heating creates temperature differences across the globe, which in turn create pressure differences. Warm air rises, creating areas of low pressure, while cooler air sinks, forming zones of high pressure. And just like water flowing downhill, air moves from high to low pressure, setting the stage for the constant movement of our atmosphere. But why does this matter? Because without these imbalances, there would be no wind, no storms,
no weather at all, juste un stagnant, unchanging sky.
So next time you step outside and feel the breeze against your skin, remember, it's not just air moving. It's the planet itself, adjusting, shifting, always seeking balance in an endless celestial dance. The pulse of pressure.
Let's dive deeper into the invisible engine driving our weather, atmospheric pressure.
Imagine standing on a mountaintop versus at sea level. What do you actually feel different? If you guess the weight of the air, you're right. Air may seem weightless, but it has mass, and all that stacked up air above us exerts pressure. At sea level, the average pressure is about 14.7 pounds per square inch. That's like having a small cat gently pressing on every inch of your body. But unlike cats, air doesn't stay still. It flows, shifts, and rearranges itself in response to changes in temperature and altitude. Think of pressure systems as the planet's way of tidying up. When warm air rises, it creates a region of lower pressure near the surface. Cooler, denser air rushes in to fill the gap, generating wind. Meanwhile, higher up in the atmosphere, that rising warm air eventually cools and starts to sink again, completing a loop known as a convection cell. These cells are the building blocks of global circulation, redistributing heat from the equator toward the poles in massive, continuous loops. But here's where things get interesting. Because the Earth spins, these circulating air masses don't move in straight lines. They curve, bend, and twist under the influence of the Coriolis effect. In the northern hemisphere, moving air deflects to the right, in the southern hemisphere, to the left. This subtle but powerful force shapes the great wind belts of the planet, turning simple convection into complex, swirling systems. From the steady trade winds near the equator to the roaring westerlies that steer storms across mid-latitudes, pressure differences and planetary rotation weave together to form the grand choreography of our atmosphere. The winds that shape our world. Now that we've set the stage with pressure and temperature, let's follow the path of the winds themselves, those invisible rivers of air that carve their way across the globe. Picture the Hadley cell, one of Earth's most fundamental atmospheric engines. Near the equator, warm air rises, creating a belt of low pressure known as the Intertropical Convergence Zone, ITCZ. As this air ascends, it cools and travels poleward at high altitudes before sinking back down around 30 degrees latitude, forming bands of high pressure. This descending air suppresses cloud formation, giving rise to many of the world's great deserts, from the Sahara to the Australian outback. But the air doesn't stop there. Once it reaches the surface, it flows back toward the equator, completing the loop. However, due to the Coriolis effect, these returning winds don't blow straight south. They curve, becoming the steady easterly trade winds that sailors once relied on to cross oceans. These winds were so predictable that early explorers used them to navigate the globe, their routes shaped as much by physics as by ambition. Further from the equator, between 30 and 60 degrees latitude, lies the Ferrel Cell, a middle latitude system that plays a crucial role in the weather patterns of North America, Europe, and much of Asia. Here, the prevailing winds flow from west to east, carrying storms across continents. These westerlies are responsible for the ever-changing skies of temperate regions, bringing everything from gentle spring rains to the dramatic winter fronts that sweep across the land. And finally, near the poles, the polar cell completes the trio of major circulation patterns. Cold, dense air sinks at the poles, forming high-pressure zones that push air equatorward. As this polar air meets the warmer mid-latitude winds, it lifts, creating another zone of low pressure around 60 degrees latitude. This boundary, where cold and warm air clash, is often the birthplace of intense storms, especially during the winter months. These three great cells, Hadley, Ferrel, and Polar, are the framework upon which Earth's global wind patterns are built. But within these broad systems lie countless smaller influences: mountains that redirect airflow, coastlines that generate sea breezes, and even urban landscapes that trap heat and alter local winds. The atmosphere is never truly still. It's a dynamic, ever-shifting system, always seeking equilibrium, always on the move.
The dance of local wind.
While the great global wind systems shape the broad strokes of our climate, it's the smaller local winds that bring daily variety to our skies. Take, for instance, the rhythm of a coastal town where the land and sea engage in an eternal exchange. During the day, the sun heats the land more quickly than the water, causing warm air to rise over the shore. Cooler air from over the ocean rushes in to replace it, creating a gentle sea breeze that whispers through palm trees and carries the scent of salt inland. But reverse the scene at night, and the pattern flips. As the land cools faster than the sea, the air above it becomes denser and begins to flow back toward the water. Now, a land breeze emerges, carrying the hush of night across the waves. These daily pulses of wind are among nature's most soothing rhythms, offering relief from summer heat and a sense of continuity in an otherwise unpredictable world. In mountainous regions, a similar tug-of-war unfolds between slopes and valleys. During the day, sunlight warms the mountain slopes, causing the air above them to rise. This draws cooler valley air upward, creating an upslope wind known as an anabatic breeze. By contrast, at night, the mountains cool rapidly, and the heavier, colder air descends into the valleys like a slow-moving river, forming a katabatic wind. These nightly downslopes can bring sudden drops in temperature, transforming a mild evening into a crisp, starlit night. Some of these local winds carry names steeped in history and culture. The Mistral, a cold, dry wind that sweeps down the Rhône Valley in France, is so fierce that homes in Provence are built with narrow windows facing away from its path. In California, the Santa Ana winds, hot, dry gusts that funnel through mountain passes, can whip wildfires into dangerous infernos, reminding us that even the most familiar winds can turn unexpectedly wild. And then there are the stranger visitors to our atmosphere. The Chinook wind, sometimes called the snow eater, descends the eastern slopes of the Rocky Mountains, bringing rapid temperature increases that can melt snow in mere hours. One moment, a landscape might be buried in white, the next, it could be bare and steaming under an unexpected burst of warmth. These localized winds remind us that the atmosphere is never truly uniform. Even within the broader patterns of global circulation, there are pockets of variation, shaped by terrain, temperature, and time of day. Whether it's the whisper of a sea breeze at dusk or the roar of a mountain gust at dawn, these winds add texture to our experience of the world, making each place feel uniquely alive.
The whispering clouds.
Clouds are the storytellers of the sky, weaving narratives of moisture, temperature, and motion. Though they appear soft and weightless, they are born from the same fundamental forces that drive all weather: evaporation, condensation, and the ceaseless movement of air. To understand clouds is to glimpse the hidden mechanics of the atmosphere, where invisible water vapor transforms into delicate wisps, towering anvils, and everything in between. It begins with evaporation. Water from oceans, lakes, rivers, and even damp soil absorbs heat from the sun and transforms into vapor, rising invisibly into the sky. As this warm, moist air ascends, it expands due to decreasing pressure and begins to cool. Cooling air can hold less moisture, and when it reaches its dew point, the temperature at which it becomes saturated, the excess vapor condenses onto microscopic particles suspended in the air. These tiny seeds, known as cloud condensation nuclei, can be dust, pollen, salt from ocean spray, or even pollutants. Without them, clouds wouldn't exist. The result of this process is a visible cloud, composed of billions of minuscule water droplets or ice crystals, depending on the temperature. Despite their apparent fluffiness, clouds are surprisingly heavy. A single cumulus cloud, the classic cotton-like puff seen on fair weather days, can weigh hundreds of tons, more than a fully loaded Boeing 747. Yet they remain aloft because the individual droplets are so small and widely spaced that air resistance keeps them suspended. But not all clouds are created equal. Their appearance depends on how the air rises and how much moisture is available. Gentle lifting of stable air produces layered stratus clouds, which stretch across the sky like a gray blanket, often bringing drizzle. More vigorous upward motion leads to cumulus clouds, those puffy towers of fair-weather cumulonimbus giants when conditions become unstable. Then there are the high-altitude clouds, formed entirely of ice crystals.
Cirrus clouds, delicate and fêtry, trace the sky like brushstroke, signaling the approach of a weather front.
Lenticular clouds, shaped like flying saucers, hover ominously over mountain peaks, sculpted by the interplay of wind and topography. And in the heart of thunderstorms, anvil-shaped cumulonimbus clouds tower miles into the atmosphere, their tops flattened by the jet stream, their bases churning with turbulence and lightning. Each type of cloud tells a different atmospheric tale, revealing whether the air is rising slowly or surging violently, whether moisture is abundant or scarce. They are both the product and the indicator of the forces shaping our skies, silently narrating the ever-changing story of the weather above us. The fall of rain and snow. Raindrops begin their journey high in the sky, where water vapor clings to microscopic particles, condensing into tiny droplets that float within clouds. But these droplets don't simply fall the moment they form. For a cloud to release precipitation, its droplets must grow large enough to overcome the resistance of the air below. This growth occurs through a process known as coalescence, where droplets collide and merge, gradually increasing in size until gravity pulls them downward. Yet not all precipitation reaches the ground as rain. In colder clouds, where temperatures dip below freezing, water vapor bypasses the liquid phase entirely, depositing directly onto ice nuclei to form delicate hexagonal ice crystals. These crystals grow by collecting more vapor or colliding with supercooled water droplets, liquid droplets that remain unfrozen despite sub-zero temperatures. As they accumulate layers of frozen moisture, they develop into the intricate structures we recognize as snowflakes. Each snowflake follows a unique path through the cloud, encountering varying temperatures and humidity levels that determine its final shape. Some emerge as slender needles, others as flat plates, and the iconic six-armed stars form only under specific conditions. When these ice crystals become heavy enough, they begin their descent. If the air below remains below freezing, they reach the ground as snow. But if they pass through a layer of warmer air, they partially melt into sleet, tiny pellets of ice that bounce upon impact. In cases where the lowest layer of air is near freezing, the droplets may remain liquid until they strike a cold surface, instantly freezing into glaze ice. This phenomenon, known as freezing rain, transforms roads, sidewalks, and power lines into treacherous sheets of black ice. Hail takes this process even further, forming exclusively within powerful thunderstorms. Strong updrafts within a cumulonimbus cloud toss ice pellets high into the storm, where they collect additional layers of supercooled water. With each cycle of ascent and descent, the hailstone grows larger until its weight finally overcomes the updraft, sending it crashing to the earth. Some hailstones, particularly those caught in persistent updrafts, can grow to astonishing sizes, some as large as grapefruits, though such extreme cases are rare. Even beyond falling precipitation, moisture finds other ways to make its presence known. Frost forms when surfaces cool below the dew point and below freezing, allowing water vapor to deposit directly as ice crystals. On clear, calm nights, these crystals bloom into delicate feather-like patterns on grass, windows, and rooftops. In certain conditions, a related phenomenon called hoarfrost creates even more elaborate structures, resembling miniature forests of ice. Meanwhile, fog, essentially a cloud at ground level, arises when air near the surface cools to the point of saturation. Radiation fog settles into valleys on clear nights, while advection fog rolls in from the sea, blanketing coastlines in ghostly mist. Freezing fog, a more sinister cousin, coats surfaces with a thin layer of ice, turning ordinary objects into glistening sculptures of frost. From the first shimmer of frost to the drumming of rain and the silent hush of snowfall, the journey of atmospheric moisture is a delicate interplay of temperature, pressure, and motion. Each drop, each flake, each icy crystal tells a story written in the language of the sky. The electric tempest. Thunderstorms are the atmosphere's grand fireworks display, a spectacle of electricity, motion, and raw energy. They begin with something deceptively simple: warm, moist air rising into a cooler environment. As this air ascends, it cools, and the water vapor within it condenses into droplets, releasing latent heat, a hidden source of energy that fuels the storm's growth. This rising column of air, known as an updraft, is the engine behind the storm, drawing in more moisture and heat to sustain itself. At first, the cloud may look harmless, an innocent cumulus puff drifting lazily across the sky. But given the right conditions, it transforms. The updraft intensifies, stretching the cloud vertically, pushing it higher and higher until it breaches the tropopause, the boundary between the troposphere and the stratosphere. Here the rising air encounters a lid of stable air, forcing it to spread outward into the characteristic anvil shape of a mature thunderstorm. Inside this towering behemoth, chaos reigns. The updraft continues to feed warm, moist air into the storm, while downdrafts, cooling air sinking under the force of gravity, begin to form. These downdrafts are laden with rain, hail, and sometimes even chunks of ice. As they crash toward the surface, they spread out in gusty bursts, creating sharp wind shifts and turbulent airflows that can knock over trees and send debris flying. But the true drama of a thunderstorm unfolds in the flashes of lightning that illuminate the sky. Lightning is the atmosphere's way of balancing electrical charges, though it does so with spectacular flair. Within the storm, tiny ice crystals and water droplets collide, exchanging electrons in a process that separates charges. Lighter ice particles tend to carry positive charges upward, while heavier hail and water droplets accumulate negative charges near the base of the cloud. This charge separation builds an enormous voltage difference, millions of volts, between different parts of the cloud, between the cloud and the ground, and even between separate clouds. Eventually, the insulating properties of the air break down, and a massive electrical discharge occurs.
D6 lightning.
The process begins with a faint, nearly invisible leader, a channel of charged particles zigzagging downward from the cloud. When this leader gets close to the ground, the electric field becomes strong enough to trigger an upward streamer from the surface. When the two meet, a powerful current surges through the channel, producing the brilliant flash we see. The air along this channel is heated to an astonishing 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun, in just a few microseconds. This explosive expansion of air generates the shock wave we hear as thunder. Lightning comes in many forms. Cloud-to-ground strikes are the most dramatic and potentially dangerous, especially for anyone caught outdoors.
Intraclou lightning dance within a single storm, illuminating the sky with flickering brilliance.
Cloud-to-cloud discharges leap between separate storm cells, connecting distant clouds in dazzling arcs. Then there are the more elusive phenomena, ball lightning, a glowing orb that floats mysteriously through the air, and sprites, jellyfish-shaped flashes that shoot upward into the mesosphere, far above the storm itself. As the storm matures, its structure becomes increasingly complex. The coexistence of strong updrafts and downdrafts creates a self-sustaining system, feeding the storm with fresh moisture and energy. But no thunderstorm lasts forever. Eventually, the downdrafts overwhelm the updrafts, cutting off the supply of warm, moist air. The storm begins to collapse, its energy dissipating as the last remnants of rain fall to the ground. Yet even in its final moments, a thunderstorm can give birth to new life. The gust front, the leading edge of cool air pushed outward by the downdraft, can lift warm, moist air ahead of it, triggering the formation of new storm cells. In this way, thunderstorms can propagate in chains, passing their energy from one generation to the next, ensuring that the sky remains alive with motion, electricity, and wonder. The wrath of nature, tornadoes and hurricanes. Tornadoes and hurricanes are the atmosphere's most dramatic expressions of imbalance, born from the relentless struggle to redistribute heat and pressure across the globe. Though vastly different in scale, both storms share a common origin: instability in the atmosphere, fueled by contrasts in temperature, moisture, and wind shear. A tornado begins as a whisper of potential within a severe thunderstorm. Most commonly, it forms within a special type of storm known as a supercell, a rotating thunderstorm with a mesocyclone, a persistent, rotating updraft. The process starts with wind shear, the change in wind speed and direction with height. Imagine surface winds blowing from the southeast, while upper-level winds come from the west and move faster. This creates a horizontal rolling motion in the lower atmosphere. When a thunderstorm develops above this zone, its powerful updraft tilts this rolling air into a vertical orientation, forming a spinning column of air within the storm. For a tornado to form, this rotation must tighten and extend downward. The exact mechanisms remain partially mysterious, but meteorologists know that subtle changes in pressure, moisture, and terrain play critical roles. Some storms flirt with tornado formation for hours, teasing the sky with rotating wall clouds but never producing a funnel. Others drop twisters with little warning. Once formed, a tornado can travel at speeds ranging from a few miles per hour to over 70, carving paths of destruction in seconds. The enhanced Fujita scale classifies tornadoes based on damage, from EF0, which might snap tree branches, to EF5, capable of leveling entire neighborhoods. Hurricanes, by contrast, are vast, long-lasting storms that form over warm tropical waters. Unlike tornadoes, which are born from a single thunderstorm, hurricanes require a combination of factors. See surface temperatures of at least 79 degrees Fahrenheit extending to a depth of around 150 feet, a pre-existing atmospheric disturbance, and low vertical wind shear. Warm ocean water evaporates, adding moisture to the air. As this air rises, it cools, condenses, and releases latent heat, fueling the storm's growth. A low-pressure center forms, and the Coriolis effect causes the air to spiral inward, organizing the system into a coherent structure. At the heart of a hurricane lies the eye, a relatively calm region of sinking air surrounded by the eye wall, where the strongest winds and heaviest rain occur. Spiral rain bands extend outward, covering hundreds of miles. Hurricanes are categorized using the Saffir-Simpson Hurricane Wind Scale, from Category 1, with sustained winds of 74 to 95 miles per hour, to Category 5, with winds exceeding 157 miles per hour. While wind is a primary danger, storm surge, the abnormal rise in sea level caused by the storm's winds pushing water toward the shore, is often the deadliest threat, especially in low-lying coastal areas. Despite their destructive power, both tornadoes and hurricanes serve a purpose in Earth's climate system. They redistribute heat from the tropics toward the poles, helping maintain the planet's delicate thermal balance. Yet in recent decades, scientists have observed changes in their behavior, linked in part to rising global temperatures. Warmer seas provide more fuel for hurricanes, potentially increasing their intensity, while shifting wind patterns may influence where tornadoes form. Tracking these storms has become increasingly sophisticated. Meteorologists use satellite data, aircraft reconnaissance, and computer models to predict their paths, providing vital warnings to communities in their wake. But despite technological advances, nature retains its unpredictability. A hurricane may weaken unexpectedly before landfall, or a tornado may defy forecasts, touching down where none was expected. So the next time you witness a storm, whether through news footage or from the safety of your window, remember that you are watching the atmosphere's attempt to restore equilibrium, a battle fought in wind, rain, and swirling fury, shaping the world in ways both terrifying and awe-inspiring. The quiet transformation, heat waves and droughts. Weather is not always loud and dramatic. Sometimes it creeps in slowly, turning up the temperature degree by degree until the air feels thick, sluggish, and oppressive. Welcome to the world of heat waves and droughts, two of the most insidious forces shaping our climate, where the absence of rain and the persistence of heat can leave lasting scars on the land and its inhabitants. Heat wave is more than just a hot day or two. It is a prolonged period of abnormally high temperatures, often accompanied by stifling humidity. What qualifies as a heat wave varies by location. What feels extreme in London might be routine in Las Vegas, but generally, it involves temperatures well above the seasonal average for at least 3 consecutive days. Some heat waves last a week, some stretch into 2, and a few can persist for weeks, reinforced by stagnant high-pressure systems that act like atmospheric lids, trapping heat near the surface. The heart of most heat waves is a high-pressure ridge, a dome of sinking air that suppresses cloud formation, allowing more sunlight to reach the ground. With no clouds to offer shade and no rising air to generate rain, the land bakes day after day. In urban areas, this effect is amplified by the urban heat island phenomenon, where concrete, asphalt, and human activity absorb and retain heat, keeping cities sweltering even after the sun sets. Trees, grass, and open soil release heat more efficiently, but city blocks hold onto it like a thermal sponge, turning nights into sleepless ovens. Humidity plays a key role in how we experience heat. When the air is humid, sweat evaporates more slowly from our skin, making us feel hotter than the actual temperature. This is where the heat index comes in, a measure of how hot it feels when humidity is factored in. If the actual temperature is 95 degrees Fahrenheit and the relative humidity is 55%, the heat index might be closer to 110 degrees Fahrenheit. That kind of heat makes asphalt sticky, turns sidewalks into frying pans, and forces people to rethink the wisdom of wearing jeans on a summer afternoon. Prolonged exposure to extreme heat isn't just uncomfortable, it can be deadly. Heat exhaustion, heat stroke, dizziness, rapid heartbeat, nausea, and confusion are all symptoms of heat-related illness. During major heat waves, hospitals often see spikes in emergency calls and admissions, especially among older adults, young children, and people with pre-existing health conditions. This is why cooling centers, shaded parks, and even well-timed fans can make a life-saving difference. Droughts, meanwhile, are the long, slow cousins of heat waves, silent and creeping, arriving not with fanfare but with the gradual disappearance of rain. A drought is defined as a prolonged period of below-average rainfall that leads to water shortages. Unlike heat waves, which announce themselves with oppressive heat, droughts build slowly, sometimes over weeks, months, or even years. Some begin subtly, with a dry winter or a failed rainy season, while others arrive suddenly, leaving parched landscapes in their wake. The effects of drought depend on geography but are far-reaching nonetheless. Shrinking rivers, cracked soil, dried-up reservoirs, and stressed crops are common signs. In extreme cases, droughts can lead to famine, forest die-offs, and even forced migration as people leave areas that can no longer support them. Drought is measured in several ways. Meteorological drought refers to a lack of precipitation. Agricultural drought affects soil moisture and crop health. Hydrological drought relates to low water levels in rivers and aquifers, and socio-economic drought occurs when water shortages begin to affect economies and societies. Several factors contribute to drought, including atmospheric circulation patterns like El Niño and La Niña, which disrupt normal rainfall patterns around the globe. Persistent high-pressure systems can also play a role, as can changes in ocean temperatures. Long-term climate shifts, particularly rising global temperatures, are making droughts more frequent and severe in many regions. As temperatures increase, evaporation rates go up, meaning water disappears more quickly from soil, lakes, and vegetation. Even when rain does return after a drought, it often runs off hardened soil instead of soaking in, sometimes causing flash flooding rather than relief. The relationship between heat waves and droughts is often circular. Drought dries out the land, reducing evaporation, which in turn allows temperatures to climb even higher. With no moisture to absorb the sun's energy, more heat goes directly into warming the air and the ground. It's a feedback loop that can lock regions into extended spells of dry, sweltering weather. Despite their challenges, both heat waves and droughts are natural parts of Earth's climate system. They have occurred for millions of years. But in recent decades, their frequency and intensity have increased in many parts of the world. Scientists attribute this trend, in part, to climate change. A warmer atmosphere holds more energy, making extreme events, including heat and drought, more likely. Adaptation to these conditions is becoming increasingly important. Cities are investing in green roofs and tree canopies to combat urban heat. Farmers are switching to drought-resistant crops and smarter irrigation techniques. Water conservation is becoming a crucial part of everyday life in places where rain can no longer be taken for granted. Still, there is beauty even in the dry and the hot. A parched landscape reveals patterns in cracked earth and wind-blown grasses. The silhouettes of trees stand defiant under a harsh sky. Heat waves can turn sunsets into fiery masterpieces as the sun dips low through a shimmering horizon. And when the rain finally returns after a long drought, it is not just weather, it is a homecoming. So the next time the air is still and the heat settles in, take a slow breath. You are witnessing the quieter side of weather, not the flashing kind, not the rumbling kind, but the kind that reshapes things in silence. Heat and dryness may not make headlines the way storms do, but their effects run deep, carved into soil memory, and the long story of the atmosphere's endless balancing act. The optical wonders of the sky. Sometimes, weather chooses to enchant rather than overwhelm. These are the gentle wonders of the atmosphere, optical illusions and subtle spectacles that remind us the sky is, at its heart, an artist. They appear in the quiet aftermath of a storm or when sunlight meets moisture in just the right way, transforming the sky into a canvas painted with color, shimmer, and light bending gently through air and water. Take the rainbow, perhaps the most iconic of all atmospheric marvels. A rainbow isn't an object you can touch or travel to, it's an optical and meteorological phenomenon, essentially a trick of light and perspective. When sunlight passes through a raindrop, it bends or refracts, then reflects off the back of the drop before bending again as it exits. This bending and bouncing cause the light to split into its component colors: red, orange, yellow, green, blue, indigo, and violet. Each color bends slightly differently, with red refracting the least and violet the most. The result is a circle of color, though we usually only see a semicircle or an arc because the ground gets in the way. From an airplane or a high mountain, however, you might glimpse the full circle hanging in midair. Double rainbows are another treat, appearing when light reflects twice inside the raindrop before exiting. The secondary rainbow appears higher in the sky and has its colors reversed, red on the bottom and violet on top. Between the two arcs lies Alexander's band, a darker band named after the ancient Greek philosopher who first described it. But rainbows are just the beginning. Enter halos, sundogs, and pillars of light, phenomena formed not by raindrops but by ice crystals in high-altitude clouds. These crystals, usually found in cirrostratus clouds, are hexagon-shaped and act like tiny prisms. When sunlight or moonlight passes through them, it bends at an angle of 22 degrees, creating a ghostly ring around the sun or moon, a halo. Halos can appear in any season but are especially common in cold weather when the upper atmosphere is rich with ice. Sundogs or parhelia are bright spots that appear on either side of the sun, often within a halo. They look like small, colorful duplicates of the sun and can be surprisingly vivid, especially when the sun is low in the sky. Like halos, sundogs are caused by ice crystals, but the crystals must be oriented just right, like tiny floating mirrors, to produce the effect. Light pillars are another lesser-known gem. These vertical beams of light appear to shoot straight up from the sun or even from street lamps. They are caused by flat plate ice crystals slowly falling through the air and reflecting light in a column. They look otherworldly, like something out of a science fiction film, but they require no aliens, just a calm atmosphere and the right kind of ice. Then there are glories and coronas. A glory is a series of colored rings that form around the shadow of your head when it's cast onto a cloud or fog bank. Often seen from airplanes, glories are created by backscattered sunlight interacting with tiny droplets in the cloud. Pilots and passengers alike refer to it as the glory of the pilot. Coronas, by contrast, form when light diffracts around individual water droplets, creating tight, colorful rings around the sun or moon. Unlike halos, coronas are small and close to the bright object, often seen through thin clouds or mist, with a compact, pearlescent appearance. Crepuscular rays, sometimes called God rays, complete the list of atmospheric wonders. These beams of sunlight appear to radiate from the sun, especially during sunrise or sunset when the sun is low and clouds scatter the light. The rays seem to fan out across the sky, but it's really just perspective at work, similar to how railroad tracks appear to converge in the distance. Crepuscular rays are caused by light streaming through gaps in clouds or mountains, illuminating particles in the air, dust, moisture, even pollen, and creating sharp contrasts that our eyes interpret as rays of divine or magical light. Finally, there's the green flash, a rare and fleeting event that occurs just before sunrise or just after sunset. For a second or two, the top edge of the sun can appear green. This happens because the atmosphere acts like a prism, bending sunlight. Blue and green light bend more than red and orange, and under the right conditions, the last sliver of sunlight may appear green. Blink and you'll miss it, but sailors and sky watchers have cherished sightings of the green flash for centuries. All of these phenomena are reminders that light and atmosphere are constantly playing together. We don't always notice the show, but when the conditions are right, the sky becomes a gallery of optical marvels, subtle or bold, fleeting or long-lasting. You don't need fancy equipment to see these wonders, just a bit of curiosity, a willingness to look up, and sometimes the patience to wait for the perfect combination of light, moisture, and timing. Whether it's a rainbow arching after a summer storm, a halo encircling a wintry sun, or a faint glory floating around your airplane shadow, each of these phenomena is a quiet whisper from the sky, reminding us that nature doesn't only work in thunder and lightning, it also speaks in color, shimmer, and light bending gently through air and water. The global tapestry of weather. Weather is intensely local. You might be enjoying sunshine while your friend a few miles away is sheltering from rain, but it is also wonderfully global. Around the world, Weather varies wildly depending on geography, latitude, ocean currents, and elevation. From the sticky monsoons of South Asia to the swirling sandstorms of the Sahara, each region has its own unique climate fingerprint. Let's take a slow and fascinating tour of how weather works around the world and how the same sky can behave so very differently from place to place. Monsoons are among the most important and dramatic seasonal weather systems on the planet. The word monsoon comes from the Arabic mausim, meaning season, and refers to a seasonal wind pattern that brings a major shift in precipitation. Most people associate monsoons with heavy rain, but a monsoon is really a large-scale wind reversal driven by temperature differences between land and sea. Nowhere is the monsoon more powerful than in South Asia, particularly India, Bangladesh, Nepal, and surrounding countries. In the summer, the land heats up faster than the ocean, creating a large area of low pressure over the Indian subcontinent. Moist air from the Indian Ocean rushes in to fill the void, rising as it hits the Himalayas and condensing into vast columns of rain. The result is weeks or even months of nearly non-stop precipitation. The monsoon is essential to life in the region. It waters crops, fills rivers, and recharges aquifers, but it can also bring dangerous floods, landslides, and disruptions to daily life. Still, it remains a welcome guest to millions, especially after the scorching dry heat of the pre-monsoon summer. Further east, places like Thailand, Vietnam, and the Philippines also experience monsoon patterns, though the timing and strength vary. In East Asia, the East Asian monsoon brings hot, wet summers and cold, dry winters, heavily influencing agriculture and urban planning alike. Meanwhile, in northern Australia, a monsoon system brings tropical storms and torrential rain to the top end during the southern hemisphere summer, usually from December to March. Locals call it the wet, and it's accompanied by stunning lightning displays and dramatic steamy skies. Now let's take a detour into the world of desert weather, a place where extremes are the norm. Deserts are often thought of as empty, lifeless spaces, but they are teeming with atmospheric action. In the Sahara, the world's largest hot desert, daytime temperatures can soar above 120 degrees Fahrenheit, while nighttime temps may plummet by as much as 40 or 50 degrees Fahrenheit. That massive swing is due to the dry air and lack of vegetation. Without moisture to hold heat, the ground quickly radiates warmth back into space once the sun sets. One of the signature features of desert weather is the dust storm, known in parts of North Africa and the Middle East as a habub. These towering walls of dust are created when cold downdrafts from thunderstorms hit the ground and push dry soil and sand into the air. These walls can stretch for miles, reduce visibility to zero, and sweep across cities like a giant eraser, blotting out the sun and coating everything in a fine layer of grit. In Australia, desert regions experience similar phenomena, sometimes with winds carrying red dust across the entire continent. In the American Southwest, dust storms are common during late summer when thunderstorm activity peaks. At high latitudes, the story changes dramatically. In the Arctic and Antarctic, weather is ruled by ice, wind, and extreme light cycles. Winters bring perpetual darkness and frigid temperatures, while summers are marked by endless daylight and melting permafrost. One of the defining features of polar weather is the katabatic wind, a cold, dense air mass that flows downhill from ice-covered plateaus. In Antarctica, these winds can reach hurricane force, sweeping snow across the frozen landscape in blinding whiteouts. Despite the cold, the polar regions are technically deserts because they receive very little precipitation. Most of the snow there fell thousands of years ago and has simply never melted. When it does snow, it often falls in the form of tiny ice crystals drifting gently to the ground, almost too delicate to notice. Heading to the tropics, where weather is as vibrant as the landscapes themselves, we find rainforests' lush environments that receive consistent, heavy rainfall year-round. Tropical regions near the equator, such as the Amazon, Congo Basin, and Southeast Asia, experience convective rainfall. The intense solar heating during the day causes warm air to rise rapidly, condensing into towering clouds that produce near-daily thunderstorms. These storms are usually short but intense, releasing bursts of rain that nourish some of the most biodiverse ecosystems on Earth. The consistency of the weather in these regions helps create the conditions for dense vegetation, layered canopies, and a constant hum of life. Travel just a bit farther from the equator, and you reach the savanna zones, where rainfall is seasonal. Long dry periods are followed by bursts of wet weather, shaping ecosystems where grasses dominate and large grazing animals roam. The timing of rains here is crucial. Too early or too late, and entire food chains are disrupted. Island nations, especially in the Pacific, experience their own unique weather systems. Trade winds, tropical cyclones, and ocean currents all play major roles. The El Niño, Southern Oscillation, ENSO, is one of the most influential global weather patterns. During an El Niño event, warm waters in the Pacific Ocean shift eastward, disrupting rainfall patterns across South America, Australia, Southeast Asia, and even Africa. In contrast, La Niña brings cooler waters and shifts weather patterns in the opposite direction. Ocean currents such as the Gulf Stream in the Atlantic or the Kuroshio Current in the Pacific also regulate climate by transporting warm water from the tropics toward the poles. These currents influence coastal temperatures and weather patterns, making places like the United Kingdom much milder than other areas at similar latitudes, and mountainous regions like the Andes, Himalayas, or Rockies, elevation plays a key role. As air rises over mountains, it cools and loses moisture, creating orographic precipitation on the windward side, where rain and snow are common. On the leeward side, the so-called rain shadow, the air descends, warms and dries out, leading to arid conditions. This is why places like the Atacama Desert in Chile, just west of the Andes, are among the driest on Earth. Coastal areas benefit from proximity to the ocean, which moderates temperature, bringing milder winters and cooler summers. Inland temperatures tend to swing more dramatically from season to season, which is why Central Asia can experience blazing summer heat and brutal winter cold, while coastal Norway, thanks to the Gulf Stream, enjoys relatively mild winters despite being far to the north. Microclimates add even more variety. A shady ravine can stay cool and moist while nearby hills bake in the sun. A city block with glass skyscrapers might reflect enough heat to feel several degrees warmer than a nearby park. A vineyard on one slope may produce different grapes than a vineyard just over the ridge. Every region on Earth has its own weather signature, shaped by a unique combination of latitude, terrain, ocean proximity, and atmospheric patterns. Yet despite all this variety, the underlying principles are the same. Heat rises, moisture condenses, air moves from high to low pressure. From the driest desert to the wettest rainforest, the rules are consistent, even if the results are wildly different. So wherever you are, whether you're watching lightning dance across a tropical sky, waiting out a dust storm in the desert, or standing in the still, silent snow of a polar night, you're experiencing one version of the same global story. A story told in wind and water, sunlight and shadow, woven through every corner of the Earth. Predicting the unpredictable, the science of forecasting. We've spent a lot of time exploring what weather is, but how do we know what's coming? How can we predict when the next storm will hit or whether it'll be sunny enough tomorrow to hang out your laundry? Weather forecasting might seem like a mix of science and guesswork, but it's actually a finely tuned art based on physics, data, and a whole lot of careful observation. It's one of the most complex tasks humans regularly attempt, and one of the most helpful. Meteorology begins with observation. To predict the future, we must first understand the present. Meteorologists rely on a global network of tools to gather. Inland temperatures tend to swing more dramatically from season to season, which is why Central Asia can experience blazing summer heat and brutal winter cold, while coastal Norway, thanks to the Gulf Stream, enjoys relatively mild winters despite being far to the north. Microclimates add even more variety. A shady ravine can stay cool and moist while nearby hills bake in the sun. A city block with glass skyscrapers might reflect enough heat to feel several degrees warmer than a nearby park. A vineyard on one slope may produce different grapes than a vineyard just over the ridge. Every region on Earth has its own weather signature, shaped by a unique combination of latitude, terrain, ocean proximity, and atmospheric patterns. Yet despite all this variety, the underlying principles are the same. Heat rises, moisture condenses, air moves from high to low pressure. From the driest desert to the wettest rainforest, the rules are consistent, even if the results are wildly different. So wherever you are, whether you're watching lightning dance across a tropical sky, waiting out a dust storm in the desert, or standing in the still, silent snow of a polar night, you're experiencing one version of the same global story. A story told in wind and water, sunlight and shadow, woven through every corner of the earth. Predicting the unpredictable, the science of forecasting. We've spent a lot of time exploring what weather is, but how do we know what's coming? How can we predict when the next storm will hit or whether it'll be sunny enough tomorrow to hang out your laundry? Weather forecasting might seem like a mix of science and guesswork, but it's actually a finely tuned art based on physics, data, and a whole lot of careful observation. It's one of the most complex tasks humans regularly attempt, and one of the most helpful. Meteorology begins with observation. To predict the future, we must first understand the present. Meteorologists rely on a global network of tools to gather. Doppler radar, in particular, can detect motion within storm systems, making it invaluable for identifying rotating thunderstorms that might spawn tornadoes. All of this data, billions of data points every day, feeds into numerical weather models. These are computer programs that simulate how the atmosphere behaves based on the laws of physics. They divide the world into a giant three-dimensional grid, with each cell representing a small chunk of the atmosphere. Within each cell, the model calculates how temperature, pressure, moisture, and wind will change over time based on surrounding conditions. The process is incredibly complex, requiring powerful supercomputers to churn through equations representing atmospheric dynamics, thermodynamics, radiation, cloud formation, and more. There are several major weather models in use today, including the GFS, Global Forecast System, in the United States, the ECMWF, European Center for Medium-Range Weather Forecasts, and the UCMET. Each model has its own strengths, weaknesses, and areas of focus. Despite their sophistication, forecasts still involve a degree of uncertainty. The atmosphere is what scientists call a chaotic system. Small differences in initial conditions can lead to big changes in outcomes. This is the essence of the so-called butterfly effect, the idea that a butterfly flapping its wings in Brazil could set off a tornado in Texas. It's a poetic way of saying that even tiny measurement errors can grow into large discrepancies over time. To manage this uncertainty, meteorologists use ensemble forecasting. Instead of running a model once, they run it dozens of times with slightly different starting conditions. The result is a range of possible outcomes, which can then be averaged or analyzed to understand the most likely scenario. If all the model runs agree, the forecast is considered high confidence. If they diverge, it's a sign that the situation is more unpredictable. Forecasts also rely heavily on human expertise. Meteorologists interpret model outputs, compare different models, consider local effects, and apply their knowledge to refine what the computers suggest. A model might not know about the peculiar way a certain mountain range funnels wind or how a particular coastline generates fog. That's where human judgment still plays a vital role. Forecast accuracy has improved dramatically over the past few decades. A 3-day forecast today is roughly as accurate as a 1-day forecast was in the 1980s. 5-day forecasts are pretty reliable, and even 10-day forecasts, while less precise, can give a decent sense of trends. Still, the farther out you go, the blurrier the picture becomes. Tiny uncertainties multiply, and the exact timing or location of events becomes harder to pin down. Short-term forecasts, sometimes called nowcasting, are especially useful for predicting rapidly evolving events like thunderstorms or tornadoes. These rely on high-resolution radar, local observations, and updated models that run every hour or even more frequently. Meteorologists use this data to issue watches and warnings, helping people stay safe during severe weather. There's also growing interest in probabilistic forecasting, where instead of saying it will rain tomorrow, a forecast might say there is a 70% chance of rain tomorrow. This approach reflects the true nature of the forecast. It's not a guarantee but a likelihood based on current information. Probabilistic forecasts help people make better decisions, whether that's packing an umbrella or rescheduling a picnic. Beyond predicting tomorrow's weather, forecasting plays a huge role in aviation, shipping, agriculture, emergency management, and energy production. Airlines use forecasts to plan flight routes and avoid turbulence. Farmers depend on rainfall predictions to irrigate crops. Utility companies adjust their systems based on expected heat or cold. Emergency responders use forecasts to prepare for hurricanes, floods, and wildfires. Weather forecasting is also expanding into the world of machine learning and artificial intelligence. These technologies are being used to analyze vast datasets, spot subtle patterns, and improve model accuracy. While they won't replace traditional forecasting anytime soon, they're becoming valuable tools in the meteorologist's toolkit. And finally, let's not forget you. Yes, you're part of the forecasting process too. With the rise of smartphones and apps, millions of people now report local weather conditions through crowdsourcing platforms. These observations help fill in gaps between official stations, providing more detailed snapshots of what's happening on the ground. So the next time you check the forecast and see that it'll be 72 degrees Fahrenheit with a 20% chance of showers, remember what went into that little icon: hundreds of satellites orbiting the Earth, balloons floating miles above the surface, supercomputers solving billions of equations, meteorologists interpreting complex data, and yes, maybe even someone like you standing in their backyard, noticing a sudden change in the breeze. It's a staggering collaboration, a global effort to read the sky, and while we can't control the weather, our ability to understand and predict it has never been better. The changing climate, weather in a warming world. Weather has always been a shapeshifter, sometimes gentle, sometimes fierce, always moving. But over the past century, and especially in the last few decades, we've begun to notice something remarkable: the weather itself is changing. Not just from day to day or season to season, but over the long arc of time. And at the heart of this transformation is a force we hear about often: climate change. To understand how climate change is affecting weather, we first need to make a careful distinction between climate and weather. Think of weather as the mood of the atmosphere, what it feels like today or tomorrow. Ici traînant? Is it hot? Is there a breeze tugging at your sleeve? Weather is short-term and highly local. Climate, on the other hand, is the personality of the atmosphere. It's the average of all those moods over a long period, typically 30 years or more. Climate tells us what's typical for a place, how much it usually rains in spring, how cold winters tend to be, how often storms roll through. Climate has never been perfectly stable. Over Earth's history, it has swung from ice ages to warm interglacial periods. These changes were driven by natural cycles, shifts in Earth's orbit, volcanic activity, solar output, and more. But what we're seeing today is different. The changes are happening faster, and they're being driven primarily by human activity. Since the late 19th century, the average global temperature has risen by more than 2 degrees Fahrenheit. That might not sound like much, but for a system as large and sensitive as Earth's climate, it's a big deal. This warming is largely due to the greenhouse effect, a natural process where certain gases trap heat in the atmosphere, keeping our planet warm enough to support life. The key greenhouse gases are carbon dioxide, methane, nitrous oxide, and water vapor. Of these, carbon dioxide plays the starring role in today's climate story. It's released when we burn fossil fuels like coal, oil, and natural gas. Deforestation adds to the problem by reducing the number of trees that can absorb carbon dioxide from the air. As greenhouse gas concentrations rise, more heat gets trapped in the atmosphere. The result is a warming planet, And that warming doesn't just mean warmer summers. It means changes in weather patterns all around the world. Let's start with heat waves, which we discussed earlier. These periods of intense, prolonged heat are becoming more frequent, more severe, and longer-lasting in many regions. Heat waves that used to occur once every 20 years now happen every few years, or even annually. Urban heat islands amplify this effect, making cities particularly vulnerable. At the same time, nights are warming faster than days. That might seem like a small detail, but it has big implications. Warmer nights offer less relief from daytime heat, increasing stress on the human body and reducing the chance for crops and animals to cool down. Precipitation patterns are shifting too. Some areas are getting wetter while others are drying out. Warmer air holds more moisture, about 4% more for every 1 degree Fahrenheit increase in temperature. That means when it rains, it often rains harder. We're seeing more extreme rainfall events with intense downpours that overwhelm drainage systems, flood streets, and wash away soil. But more moisture in the air doesn't guarantee more rain for everyone. Some regions are becoming drier, especially those already prone to drought. Longer dry spells, combined with higher temperatures, lead to parched soils, shrinking rivers, and stressed ecosystems. In places like the southwestern United States, southern Europe, and parts of Africa, droughts are becoming more frequent and severe. This pattern, more extremes in both directions, is one of the hallmarks of climate change.
Wet area get vetter, der y area get drier.
It's not a simple warming, it's a reshuffling of the entire system. Storms are also changing. Warmer ocean temperatures provide more energy for tropical storms, which can lead to stronger hurricanes, cyclones, and typhoons. There's evidence that while the total number of storms each year hasn't increased dramatically, the intensity of storms has. We're seeing more Category 4 and Category 5 hurricanes, storms capable of catastrophic damage. These storms also hold more moisture, which means more rainfall when they make landfall. Hurricanes like Harvey in 2017 and Florence in 2018 dumped astonishing amounts of rain, causing widespread flooding even in areas far from the coast. Further north, winter storms are also being affected. A warmer atmosphere doesn't mean we won't have snow. In fact, it can mean more snow in some places because the air can carry more moisture. But the timing and nature of winter weather are changing. Snow seasons are starting later and ending earlier. Snowpack, which acts as natural water storage in mountain regions, is shrinking. Climate change is also altering the jet stream, the high-altitude river of wind that helps guide weather systems across the globe. As the Arctic warms faster than the rest of the planet, a phenomenon known as Arctic amplification, the temperature difference between the poles and the equator weakens. This can slow down the jet stream and make it wobble, leading to unusual weather patterns. A slower, wavier jet stream can cause weather systems to stall. That means a rainstorm might linger over the same region for days, or a heat wave might lock in place. These stalled systems have been linked to several recent extreme events, from European heat waves to prolonged flooding in the United States. Sea level rise is another consequence of climate change. Though it's not weather in itself, it profoundly affects how weather is experienced, especially in coastal areas. As glaciers melt and oceans warm and expand, sea levels are rising by about 8 inches since the late 1800s. Higher sea levels mean that storm surges and tidal flooding are more destructive, reaching farther inland and affecting more people. Climate change also influences wildfires, not directly through flames and smoke, but through the conditions that allow them to ignite and spread. Hotter temperatures, drier soils, and earlier snowmelt create longer fire seasons. Lightning strikes, one of nature's ignition sources, may also increase with more convective storms. Once a fire begins, high winds and dry vegetation allow it to spread rapidly. The result is more intense, more frequent, and more damaging wildfires in many parts of the world, from California to Australia to Siberia. These changes don't mean that every weather event is now caused by climate change. Weather will always be variable. There will always be cold snaps, rainy days, and mild seasons. But what scientists can now do is study how climate change increases the likelihood or intensity of specific events. This is called attribution science, and it helps us understand how the background conditions of a warming world are shaping what the atmosphere delivers. So what can be done? First, it's important to recognize that not all change is inevitable. While some warming is already baked in due to past emissions, future outcomes depend on choices we make today. Reducing greenhouse gas emissions, switching to renewable energy sources, improving energy efficiency, protecting forests, and changing how we grow food and use land can all help slow the pace of change. Adaptation is also key. Communities are redesigning infrastructure to handle heavier rains, planting trees to cool cities, and updating building codes to withstand stronger storms. Farmers are experimenting with drought-resistant crops. Cities are mapping flood zones and building seawalls. Individuals, people like you, are learning how to stay safe during extreme heat, conserve water, and reduce their carbon footprint. Even small actions matter when multiplied across millions of people. Those actions become powerful: walking instead of driving, turning off unused lights, supporting policies that protect the environment. These things add up, like raindrops in a storm. The weather is still the weather, capricious, beautiful, unpredictable in its details. But the canvas it paints on is changing. The boundaries have shifted, the stakes have risen, and we are both observers and participants in that change. So the next time the sky darkens unexpectedly, or the summer feels just a bit too long, or the rains come harder than usual, remember, you're witnessing not just weather, but a chapter in the larger story of a planet in transition. A story still being written by wind, by water, by people, and still very much within our power to shape. Close your eyes again if you like. Let your thoughts drift like clouds. Somewhere far away, a breeze is flowing silently over mountaintops. Raindrops are gathering on leaves. A snowflake is beginning to fall. It's comforting in a way to know that the sky never truly sleeps. It simply shifts, reshapes, and continues its slow dance above us. Thank you for being here tonight. Thank you for winding down with me and joining this journey through the science of weather. Wherever you are, whether you're listening from midnight, from 2 o'clock in the morning, or from a quiet afternoon with the curtains drawn, I hope this helped you relax, sparked a little curiosity, and reminded you of the quiet wonder that surrounds us, even in the simplest breath of air. This felt like a peaceful escape. Please consider liking the video or subscribing to The Silent Scientist. It means a lot, and it helps others find their way here too. Rest well, let your thoughts drift, and may your dreams be as soft as fog and as bright as a morning after rain. Good night.